So what we have done in the previous turn, we have already seen some devices, and those devices we have seen the physical layer devices like repeaters and hubs. And what else we have seen? We have seen layer 2 switches, bridge, and the working of those devices. Now what is the agenda today? uh, the agenda for today is, agenda 1 is that I will be telling you about the layer 3 device, and I have already started a brief introduction about layer 3 device, and I have already provided you the IP address mechanism and the classes of IP address. I've already explained that in IP version 4 there are different octets, which are like 4 octets are there: 32-bit IP address, 32-bit IP address, and those are represented as a dotted decimal notation, where every octet is 8-bit. And then I have given you classes of IP address, that in class A the first octet is network part and rest is host part. In class B, first 2 octet are the network part and rest 2 octets are the host part. And in class C, first 3 octets means 24 bits in network part and 8 bits in the host part. This we have already done. Now let's see what is the use, why we require a layer 3 device, and what is the working of layer 3 device. Now suppose I say that there is a huge network, and let me draw a network with the help of layer 2 switches. So L2 switch, then this L2 switch might be connected to another L2 switch, another L2 switch. Fine, don't worry, you'll get the recording later. Okay. So I'm doing the recording on OBS. Okay. So I'll share the lectures later on. Getting the point? Okay. So this is L2 switch, L2 switch, L2 switch, and we can again connect some L2 switches. So I'm trying to give you a visualization of a huge network. Fine. So many L2 switches are connected, and then your hosts are connected. Fine. Now suppose I want to broadcast. So a node here want to broadcast a message. Broadcast means purposely a node A, suppose this node, wants to send message to all other nodes which are connected at the last layer of L2 switches. Now I haven't told you one thing, that in every IP address there are 2 spatial IP addresses, and those IP addresses are reserved in every IP address. Suppose if I say that there is a class C IP address, class C IP address, so you know that in class C IP address 24 bits 24 bits network part, and then 8 bits host part. So this is okay, means any class C network IP address can have 2 to the power 8 host addresses, means 256 host addresses. Now these 8 bits can have combination like this from all 0 to all 1. These 8 bits have combination like this. So the first combination all 0 is reserved. This is reserved. And the last combination of all 1 is again reserved. So if all host bits means the bits in the host part are zeros, then this IP address is known as network address, and this address cannot be given to any host. If all host bits are 1, then for that network, this IP address where all the host bits are 1, it is known as broadcast address. Means that if I want to broadcast in my network, so another way is that you send different messages to all different machines, or you use a broadcast address, and that address, once it reaches to the L2 switch, it will be forwarded to all the nodes, so on and so forth. So in every IP address, there's going to be 2 parts. One is host all 0 and host all 1. So if I say that 192.168.10. This is something IP address, this is class C IP address, and I know in class C IP address last 8 bits are host part, so .0 will be the network ID and .255 would be broadcast ID. And from .1 to .254 means 254 addresses are valid host addresses. So if somebody asks you a question that how many valid host addresses are there in any class C network, so you will say that 2 to the power 8 minus 2, because one is for network ID and other is for broadcast ID. Now this is one important takeaway in any IP address. Any IP network, if it is a network, you need to know about what is the network ID. So how to know about the network ID? Go for the host part and put all zeros in the host part, you will get the network ID. Go to the host part, put all ones in the host part, you will get the broadcast ID. In a class C IP address, in a class C network, all 8-bit 0 it is a network ID, and all 8-bit 1 it's a broadcast ID. Okay. Now if this is clear, then there's another important thing which is known as subnet mask. And I'll come back to this. So just a little bit of information at this particular point, and then I'll be coming back to this in detail. Now what is a subnet mask? Any IP address you put once in network part and put zeros in host part. If you do like this, then you'll get the subnet mask of that network. Now if I take class C, so in class C we know that 24-bit network part, so if we put all ones in network part, so class C network mask would be 255.255.255.0. So this is network part. We have put all ones. It will result into 255.255.255. This is the host part. We'll put all 0. This will result into 0. This is class C. If you go for class A, so network part is 8-bit. So class A subnet mask would be 255.0.0.0. For class B, so network mask would be what? Yes, Abhigyan? In class B, what would the next network mask? .255.0.0, because we know that in class B this is network part and this is host part. Okay, now let us assume a situation where and this is a very common situation in the context of how the networks are designed and how the networks are administered. This is a very normal situation. And what is, suppose there is a class C network. Means this class C network can have 254 hosts maximum. Now if I use broadcast ID, so suppose I say that class C network is 192.168.10.0, and this is the network ID because all 0 are there. And what is the broadcast ID? Broadcast ID would be 192.168.10.255. And if any host of this network uses this as a destination IP address, that particular packet will be delivered to all the hosts which are connected in the network, and that's the meaning of the broadcast IP address. Now let's assume that I don't want to do that. Suppose this class C network is, say, one company is there or one organization is there, and that organization functions in 4 different departments, maybe account, management, engineering, audit, 4 different departments. So if I say that engineering fellow want to limit their broadcasts in the nodes which are in engineering department only, audit fellow wants to limit their broadcasts in the nodes, among the nodes which are in audit department only, and so on and so forth. So what is the solution? Because if you use a broadcast address like this, which is a broadcast, when anybody sends, that will be transferred to everywhere. But you don't want to do that. You want to limit. The technical aspect is you want to break the broadcast domain, or you want to divide the broadcast domain so that your broadcasts can be limited within the department. So it is a scenario like that. There is a big network, whole organization network, and actually that network, you need to divide that network into 4 smaller sub networks. Having said that, for outer world, this is one network. The fellows who are outside this organization will visualize this network as one network. But within the organization, you have to divide this network into 4 sub-networks. If we take this particular case, where there are 4 departments. Now, what is the way out? What is the way out? And this is most important, because related to this there are so many questions and queries might be there in your mind, and that's why I'm taking this particular topic before starting computer networks from top down. So I'm trying to resolve many curiosities and queries which are already there in your mind. Now, the technique which we need to use, that technique is popularly known as subnetting. That technique is known as subnetting. Now, what is subnetting? It's very simple, and whole process is mechanical process. You just need to follow that process once. So if I say that there is a network 192.168.10.0, so class C network, and I want to divide into 4 subnetworks, then what I need to do? I need to extend the network part of this network address. And because I want to have 4 subnetworks, let us borrow 3 bits from the host part. Why I haven't borrowed 2 bits? I'm just coming to that. And extend the network part from 24 bits to 27 bits. Obviously, when you divide the network, those smaller subnetworks would be having less number of nodes. And that's the process known as subnetting. Now you might be thinking that if I want to have 4 subnetworks, why I haven't borrowed 2 bits? Suppose if you borrow 2 bits, 0, 0, so these 2 bits can have 4 combination. These 4 combinations, fine. So if you take first combination 192.168.10.00, suppose I take the first combination here, and now consider these 26 bits in the network, then my network would look like this: 192.168.10.00, and rest 5 bits can move from all 0 to all 1. Sorry, 5 bits, 1 2 3 4 5. So let me rub this last. Okay, now net host part all 0 means network ID. So my first subnetwork ID would be 192.168.10.00. This is network part, and all host bits, because now the host bits are 5, all host bits are 0. There again 1 2 3 4 5 zeros. This is host bit, but if you take all these bits together, this is again 0. So overall network ID will be clashing with the first subnetwork ID. Similarly, if you take the last combination, so if we take last combination, so 192.168.10.11 and rest 5 bits are, let me draw it here. So if I take 192.168.10.11, so this is the network part now. Rest 5 bits all 0 and all 1. Now if you take the all 1 in the host part, so if host part, which is now 5 bits, if host part is all 1, it means it's a broadcast ID. So broadcast ID of the last subnet, would be what? 192.168.10.11. This is network part, then 1 2 3 4 5, this is host part. This together if you take, this is again 255. So in this case, the broadcast ID of the last subnet would be clashing with the broadcast ID of the overall network. And that's why we haven't borrowed 2 bits. We have borrowed 3 bits from the host. If we have borrowed 2 bits, then this might be the, just a minute, I have to take this call. हेलो सर, क्लास ले रहा हूँ अभी. Okay, so now you get the reason that why we have taken 3 bits, why we have borrowed 3 bits instead of 2 bits. Because if we take 2 bits, the first subnetwork ID would be crashing with the overall network ID, and last subnet's broadcast ID will be crashing with the overall network's broadcast ID. So let's subnet the network. 192.168.10.0000, say 8 bits. Let's borrow 3 bits. Now your network is extended to 27 bits. These 3 bits can have this combination. So as evident now that we'll not be taking the first combination and the last combination. So remaining combinations are these. So let's take the first combination. 192.168.10.001. Fine. Network part. and rest 5 bits all 0 and all up to all 1. So what is this number in decimal? 0 1 2 3 4 5. What is this number? 1 5 0 0 1 2 3 4 0 1 2 3 4 5. It is 192.168.10.32. This is our first subnet ID. First subnet ID. What is this number? Tell me. So dot 63 would be the broadcast ID of first subnet. ID of the first subnet. And from 33 to 62 would be the valid host IDs. Now let's take the next combination. If we take the next combination, it would be 192.10.010 all zeros to all ones. What is this number? 64. So dot 64 would be the second subnet ID. Dot 95. What is this number? Dot 95. 95 would be the broadcast ID of the second subnet, and from 65.65 to .94 would be the valid host ID. Similarly, the next subnet will start from 96. It will go up to 127. Next subnet will start from 128 and it will go to what? 149 or 59? 159. Fine. And so on and so forth. In this way, you can have different subnets. Now, let me draw the overall picture. Fine. Control all. Delete. Now, let me draw a topology. So, there is we need a layer 3 device. And with this layer 3 device, I have connected L2 devices. We have got 4 departments, L2, and from L2 the nodes are connected. So let's say that this is our first subnet. So our subnet ID was .32, yes, and broadcast ID was .63 and host ranges are .33 to .62. Okay, and overall network is 192.168.10.0. Our first subnet ID is 192.168.10.32. Fine. Now let me do one more tweak. The first valid host ID, this IP address .33, let me give this IP address to this router interface. or the layer 3 device interface. So here I'll assign IP address of this interface as dot 33. Why? Just let me explain in a moment. Now suppose this is our second subnet. So second subnet dot 64 to dot 95. First valid host ID dot 65. Let me assign to this. Let me assign to this dot 65. Suppose this is our third subnet. So dot 96 to dot 127, and dot 97 would be the first valid host. Let me assign it here dot 97. This is suppose our fourth subnet, so it is dot 128 to dot 159, and let me assign dot 129 to the layer 3 interface. Now you can see here the whole network is divided into 4 subnet, where this interface of layer 3 is part of subnet 1. If we draw like this is second subnet, and this interface of layer 3 device is part of second subnet, and so on and so forth. Now if you see your LAN card setting, and let me show you the LAN card setting. If I go to network and internet setting, you can see that. So if I go and see the connection setting, you can see in your machines. So and go to the TCP IP4 properties. Is it visible to everybody? You can see the, if you see the properties TCP IP version 4, and you see that my machine is having one IP address. I'm in one subnet somewhere in institute. My machine is having a subnet mask, and my machine is having another setting, that is default gateway. So in any organization, if there is a static IP address assignment, you need to provide these 3 entities to every machine: the IP address of the machine, the subnet mask, and the default gateway. Now you may be getting some hints here. So here every machine is having a IP address now in this network. So let's take any machine in this subnet, and it might be having IP address 192.168.10. say 37. So in this subnet every machine would be having IP addresses starting from dot 34 to dot 62, because the first valid IP address is given to the router interface or the layer 3 device interface. Now let's come to what is subnet mask of this machine. So subnet mask is very easy to find out, because you know that when you want to find out subnet mask, put all ones in the network part, and put all zeros, all ones in network part, and all zeros in host part. All zeros. So our network part is what now? Our network part was 24 initially, which was extended by 3 bits. So our subnet mask would be 255 first 8 bit, 255 next 8 bit, 255 another 8 bit, and then it is 111.000.00. And what is this number? 224. Tell me. 24. So the subnet mask for this machine, and almost actually every machine, the subnet mask would be 255.255.255.224. And next entity is default gateway. So for this subnetwork, now please pay attention, for this subnetwork, the machines in this subnetwork, the default gateway is this IP address, which was assigned to the layer 3 device or router interface connected to your network. So default gateway for this machine in this subnet would be 192.168.10.33. Default gateway for this subnetwork machine would be .65, because we have assigned the first usable address of the subnet to the gateway or the router interface connected to your subnet. So this is the methodology of designing a network, that you need to provide IP addresses to every machine, then you need to provide subnet mask, and then you need to provide the default gateway. What are the utility of these entities? I'll be just coming to that, don't worry. Now, please be with me. Now, if I take any IP address, give me any IP address from this. Now, suppose I take any IP address like 192.168. say 10.100. Can anybody give me 192.168.10.100 in binary? One person? 100 in binary in 8 bits? Okay, in 8 bits, 0 double 1 double 0 1 double 0. So this is 100. Now let's take the subnet mask. So let's take the subnet mask of that subnet. So 192.160, sorry, subnet mask is something else. So subnet mask would be 255.255.111.00000. And let's do the bitwise AND operation. So this is all one, okay? And if you do bitwise AND, this will result into what? 192. You do bitwise AND with all 1, it will result into 168. You do bitwise AND with 10 and all 1, it will result in 10. Now you do the bitwise AND operation, it is 0, 1, 1, and then all 0. So what is this number? What is this number? 0.96. Means if you do bitwise AND operation with subnet mask, you'll get the network ID. You'll get the network IP address of that subnet. Means if you want to know which subnet this IP address belongs to, you need to use your subnet mask and do the bitwise AND operation. Fine. So subnet mask is used to know the subnet of any machine. Now, is there any question from anybody? I'm ready to answer. Is there any question from anybody? Karimullah? Why should you do that? That's a bad design. If it is connected into one L2, then there are techniques to do that. That is known as virtual LAN. Fine, VLAN will be coming to that. Okay. You can have two different subnets connected into one L2 switch, but I don't think that right now this is in your scope, and you are thinking in that direction of virtual LANing. Fine, it is possible, but that is a very very advanced topic, and we'll be coming to that maybe after 1.5 months. Okay. Right now, yeah. Hmm. Yeah, because I have taken the IP address. Our default network was 192.168.10.0. This was the class B class C network, and the range of this class C network was from dot 1 to dot 254. I have taken any IP address from this network, and we have divided the network into many subnetworks, and I wanted to know which subnet this dot 100 may belong to. So I have used subnet mask and did the bitwise AND operation. I get to know that this belongs to this dot 96 subnet. Got the point? So I think you might have slept for a while, because when you want to have subnet mask, the rule of subnet mask is all the network part, all the bits in the network part would be 1. So our initial network part was 24 bits. We have extended our network part by 3 bits, and now our network part is 27 bits, and that's why in subnet mask we have 24 ones and then 3 ones. Got the point? Any other question? Mm-hmm. Maybe you can have different subnet masks for different because look, that's again a bit advanced. So I'm not saying right now, I'm just talking about a network and a subnetwork. What you are talking about, a network, a subnetwork, and within that subnetwork another subnetwork. Are you getting the point? As you increase one more bit, means you are going inside that subnetwork. Okay. So that is again will be covered later on. We'll be doing this thing, that a big network, then like you can do like that. We have right now at the first level only. So a big network having 4 subnetworks. Okay. You can very well take this subnetwork and again divide into 4 subnetworks. Okay. And the subnet mask of this may is larger than the subnet mask of this subnetwork, and your case will come that okay, it might be matching with all four ones also. Then there is another mechanism that we always go for the longest match if we want to pinpoint that whether it is in the outer subnet or any other inner subnet. That's a longest match. That's again a bit advanced, and we'll be coming to that, don't worry. Yes, any other question? Any other question? Okay, if there are no question, then let us proceed. Now the question here is, the next aspect here is, let me draw the topology again, maybe the half of the topology. So this is L3, then L2, then our nodes, again L3, then L2, and then our nodes. So let me draw the half topology only. Now the question here is that suppose there is a node, let me take one case study 1, and then case study 2 will be taken after that. So there is one node A wants to transfer data to another node B. So this is case study 1, where apparently pictorially we can see that two nodes in one subnet wants to transfer data. And then the next case study, that this node A wants to transfer data to any node C here, which is pictorially looking like another subnet. So let's stick to case study 1, case 1, where nodes within one subnet wants to transfer. Now, as I told you that we require 6 identifiers for data transfer, and those 6 identifiers are source port, destination port, which are transport layer stuff. So for example, you can say that A is a browser and B is a web server, and browser wants to fetch a page from this web server. So source port can be given by the browser's operating system, A's operating system, say 5082, any source port, 2 to the power 16 source ports are there. Destination port, we know that web server is HTTP server, which runs over TCP and listens on port number 80. There are some well-known port numbers. And for well-known protocols, and HTTP server always listen at port number 80. So source port, destination port is done. Now source IP and destination IP. Let's assume that A knows the IP of B. Suppose A is 192.168.10.38 and B is 192.168.10.47. So we know the source IP and destination IP. So this is done. Source MAC. Source MAC, A knows the source MAC because A knows the MAC address of its own. The source MAC is done. Destination MAC address, that's the question. And until unless we have destination MAC address field filled, our packet will not go out of a machine. Forget about how it will transfer in the network. So that's the biggest issue, that how to know the destination MAC address. And for that purpose, if I draw the protocol stack, so at the top we have application layer, then we have transport layer, then we have network layer, then we have MAC or data link layer, then we have physical layer. Now to know the destination MAC, there is a protocol known as ARP, Address Resolution Protocol, and the placement of ARP is here. You can assume that it is in between network layer and MAC layer. ARP is placed here. ARP is not application layer protocol. Now what ARP? Because ARP starts here, so ARP, if ARP wants to send any message, ARP does not require source port, destination port and other things, because ARP is starting here. In detail, ARP will be covered later, but in simple aspect, what is ARP? ARP just asks one question. Just asks one question. What is the MAC of this IP address, destination IP address? Because we know the destination IP address, but we don't know the destination MAC. So what is the MAC of? And then there is a special purpose MAC address where all 48 bits are 1, and if I write in hexadecimal means all F. This is known as special purpose MAC address, known as broadcast MAC address. If in destination MAC this address is there, broadcast, then L2 has to forward it to all the connected ports. So ARP will form a packet. So ARP has just to give source MAC of machine A, maybe MAC of A. In destination MAC, it will give all F, and now ARP protocol is running. So before any data can be transferred, A will run a ARP protocol. So destination MAC, and in ARP protocol, when ARP sends a ARP request packet. So in ARP request packet, the source MAC would be MAC of A, the destination MAC would be all F, and in question there would be IP address. What IP address? This one, which is destination IP address. Now this ARP request, obviously A will transfer to switch. Switch will extract the packet and found out that destination MAC is all F. This will be forwarded to all the ports because this is a broadcast MAC address. And every machine which is connected to L2 has to receive and accept both this packet, because this is a broadcast MAC address. Every machine will be receiving this packet. Every machine there is a ARP daemon running. Every machine runs a ARP daemon. Operating system runs a ARP daemon. So this ARP request will be transferred to the ARP daemon of each machine. And then the machine which is having this IP address will say bingo and will send a ARP reply that my MAC address is this, whatever. ARP reply is, again, because ARP runs at just above MAC layer, ARP reply would be having source MAC of machine machine B, because now ARP reply is going from machine B. Destination MAC would be destination MAC address of machine A because machine A has sent the ARP request, MAC of A, and that is how machine A will be knowing the MAC address of machine B, destination MAC address. And now all the fields are complete. So a packet will be formed and packet will be transferred to layer 2 switch. Layer 2 switch will extract the destination MAC field, will find out the MAC address of machine B, and the data will be transferred to machine B. And hence our case 1 is over. Any questions? Any questions from anybody? Yeah. Means for every packet you will send every packet to all the machine in the whole network of Motilal. Just take example. Means every packet will be going everywhere. You store the IP at L2 or you store the MAC at L2? You store the MAC at L2. Why at L2? We can have a ARP cache at every machine. Okay? And because but once you need to run, so let me show you the ARP cache of my machine. CMD. Is it visible? So these are the machine I keep on talking. Fine. So for these machines, I need not run ARP again and again because the MAC address is already cached. Got the point? But suppose if I want to communicate to a new machine, then I need to run that ARP. Okay? Okay, bacha? Okay. Any other question? Now let's take the another case. Let me draw the topology again, and so let me draw the L3, then L2, again one L2. So there are nodes. So this is suppose our first subnet. There is a one machine 192.168.10.37, and now it wants to communicate to a machine 192.168.10. Say this is the second subnet, say 72. Now please pay attention everybody, this is important. Please pay attention everybody. So as one person was saying that, so the first step, if you don't know the, obviously you don't know the destination MAC address. Destination MAC address is not known most of the time. If you don't know the destination MAC address, you go and look into ARP cache. If it is available there, okay. Otherwise, the next step is, the first step is go and look into ARP cache. The second step is you need to know where is the destination. In the previous case, it was very easy pictorially. You know that destination is in your own subnet because pictorially B was placed here. Here also pictorially you can know that C is placed in another subnet, but how machine will be able to know? A machine will be able to know where is B or where is C. So the second step is I am giving you a naive method to know where is the destination. There is a proper methodology also, but that will come later. So the naive method is just use your subnet mask. Suppose source is 192.168.10.37 and destination right now is 192.168.10.72. Give me the binary of 37 in 8 bits and 72 also. Anybody? 0100 10 8 bits I want. Eight, 2, 3, 4, 5, 6, 7 0100 4 bits 10. Give me the right answer. So 0010, okay? 0010 0101. This is 37. What is 72? Yeah. Okay. 20 1 000. Okay. So what machine A will do? Machine A will take its own address and do the bitwise AND operation with its subnet mask. So subnet mask is 255.255.255.111 all 0. The answer would be what? 192.168. Now you'll be knowing that answer would be .32. Okay? Because subnet mask will give the subnet ID and subnet ID was .32. When you do the subnet masking with destination, apply subnet mask over destination, you'll get what? You'll get 64. Yes or no? Check it up. So this is the second step. Machine A will use the subnet mask to know the subnet of itself and the destination. If these two entities are coming different, then it means that destination is in another subnet, and then the whole concept changes. If these two things means what subnet mask is doing, subnet mask is giving you the network ID, and now you know that destination's network ID is this and source network ID is this. There are two different things. Now even if you do the ARP broadcast from A to know the MAC address of destination C, the broadcast will not cross layer 3, because that's why we have a layer 3 device. That's why we have done the subnetting to break the broadcast domain. Layer 3 device never forwards any broadcast. So even if you do the broadcast, ARP broadcast for the destination, that okay, destination IP is this, and to know the MAC address, let us do the ARP broadcast, that will be stopped by L3. And that is done deliberately because we don't want ARP broadcast to be, moving in whole network, and for every thing we need ARP broadcast, so our network will be bogged down by the ARP broadcast only. That's why we have to have subnets. So your ARP broadcast, if you do, will not reach here. Now please don't sleep and be with me. Now what is the answer? Answer is simple. Don't try to send packet directly to the destination. Just try to send packet to the L3 device first. Now if you want to send packet to L3 device, please be with me. Source port, destination port is same. Suppose this is web server, C is web server, so any source port and then destination port 80. Source IP, destination IP will remain same. Source IP will be .37, destination IP will be .72. Source MAC would be of machine A. Destination MAC we don't know. We cannot know also because destination A is in another subnet. So what's the way out? Just try, please be with me, try to get MAC address of default gateway. And your machine is having default gateway also. And what is the default gateway? The first usable IP address, this interface IP address of L3 device is the default gateway. Mind you, don't change the destination IP. Destination IP will remain same, .72. But instead of running ARP for .72, run ARP for your default gateway, which is what? In our case, it is .33, this side. And your ARP will reach up to this point. ARP request will reach up to this point because this .33 interface is part of your subnet. Do the ARP request. ARP request will be sent here. Destination is in question will be default gateway IP address. Tell me the MAC address of default gateway IP address. That will be the question in ARP request. So ARP request will reach to L2. L2 has to forward it because it's ARP broadcast. L2 will forward this side also. It will reach to default gateway, or it will reach to this interface of L3 device. L3 is also running ARP daemon. Now L3 will respond with the MAC of DG, default gateway. L3 will send ARP reply and MAC of default gateway will come to machine A. Now what machine A will do? That's interesting. Instead of giving actual destination MAC address, it will put MAC address of default gateway. Knowing that I'm not actually writing the ultimate destination MAC address, because ultimate destination is another subnet, so there is no other way. The way out is to just somehow send the packet to the L3 device. So destination IP would be the actual destination IP address, but destination MAC would be the MAC of default gateway, and default gateway of your side is .33. Now packet will be sent. Packet with this information, packet with these details will be sent to where? To L3. what L3 is going to do? What L3 is going to do? L3 will receive the packet. Why L3 will receive the packet? Because L3 will extract the outermost header. It will find destination MAC which is matching with the MAC address of this interface, because you have put MAC address of default gateway. So the outermost header will be having destination MAC and source MAC. Outer MAC header will be having destination MAC of default gateway, means destination MAC of this interface. Now outer header will be removed after accepting the packet. Next header will be opened. Next header would be having source IP and destination IP. Source IP and destination IP, and now we'll extract the destination IP address. Please be with me. Please be with me. Now we will extract the destination IP. And because outer header is removed now, the packet will be transferred to the network layer of L3 device. L3 device is L3 because it is having physical layer, data link or MAC layer, and network layer. So after extracting and after receiving the packet, the outermost header, Ethernet header, will be removed and packet will be transferred to the network layer of L3 device. We have done the decapsulation of the outermost header and packet will be transferred to the network layer of L3 device. Now at L3 device, again there is a table, forwarding table known as routing table. So let me draw the L3 device here first. Suppose there are 4 interfaces. Let me name the interfaces. Say ETH1, ETH2, ETH3, ETH4. Here we have connected subnet 1.32. Here we have connected subnet 2.64. Here we have connected subnet 3.96. And here we have connected subnet 4, that is 128. So what is there inside the routing table? I'm just drawing a very generic routing table. So in routing table there is destination, networks, first field, the networks which can be reached from this device, destination networks. Second field, subnet mask. Third field, through which interface of this device you can go to that network, the interface. I'm just drawing a very minimal routing table just to make you understand. So in this L3 device there are 4 destinations: 192.168.10.32.64.96.128. See here we are not writing any host IDs, we are writing the network IDs. And that's the utility of network IP address, because L3 devices and router does not contain any host IPs, they contain the network IPs. Subnet mask, same. In this example, because the size of subnets is same, the subnet mask is same, where in last there is .224, .224, .224, so .32 is reachable via ETH1, Dot 64 is reachable via eth2. Dot 96 is reachable via eth3, and dot 120 is reachable via eth4. So I have populated the routing table. Now what is transferred from layer below after extracting the outermost header and after receiving the packet? Source IP and destination IP. So we are interested in the destination IP. What is the destination IP in our example? If I remember correctly, 192.168.10.72, is it? 72. So what we'll do, we'll extract the destination IP from the network header, network layer header, and now we'll apply the subnet mask. Here all the entries are having same subnet mask. If you apply this subnet mask, you know what will be coming. If I apply and do the bitwise AND operation, what will come? Dot 64 will come after applying subnet mask, which will be matching with this entry. So L3 will switch this packet inside from here to here, eth2. Now let's see at eth2 what will happen. At this interface, what will happen? So packet has started from this subnet, it has reached to eth1. eth1 has received the packet because it is having MAC address of this interface. Outer header was removed. Packet was transferred to the network layer of L3 device. There we have done the matching of destination IP address in the routing table, and somehow we are here now. So again, packet will be reformulated. Packet will be repacked. So we require source port, destination port, which is already there in the packet. We haven't touched the transport layer header. Source IP, destination IP remains same in the network header. Source MAC will change. Now source MAC will be the MAC address of this interface eth2. Okay. And destination MAC again not known. But now the things are easy because now the packet is at eth2, which is part of this subnet. Now the packet has eth2, and eth2 is having the first usable IP address of this subnet, that is .65. Means eth2 is part of this destination subnet. Now eth2 can run ARP request for the actual destination .72. So ARP broadcast will go to L2, will be broadcasted to all the machine. .72 wala machine will reply with its own MAC address, and now destination MAC address is known, and packet is forwarded further from the L3 device, which will reach at 10.72. So there are steps in this case. First of all, the packet will be transferred from source to the L3 device, and initially you will put the MAC address of your default gateway. Then using a routing table, packet will be routed to eth2, the destination interface. We still don't know the actual destination MAC address, so this interface, the destination interface, will run ARP to know the MAC address of actual destination. Source MAC address will also change because now eth2 is actual source which is transferring packet. So source MAC will be of eth2 and destination MAC will be known when eth2 runs the ARP, and This is how data transfer is done. Any questions or doubts? Karimullah? You are not asking a good question. You are saying L2 and you are saying why don't we store IP? L2 is L2, no layer 2 device. So, and your packet will not be having MAC address then, huh? That's the second aspect. That's another aspect. The question is why we are using Mac. It started from that discussion when we actually didn't want to disturb our kernel when we were having Ethernet and shared media. Remember? Got it? So Mac is a kind of backward compatibility thing. Okay, it's a evolving technology. You just cannot have a one flag day and say that now we're not going to use Mac anymore. No, this is part of our protocol stack. That's another story. Due to switched Ethernet, now you don't have collision and you don't use CSMA CD, but MAC address is there. MAC has to be there. Okay. And I'll tell you later on, within a subnet, actually, you don't require IP address to forward the data. That's another beautiful thing. If you want to transfer packet within a subnet, that's a very beautiful thing. Suppose I say that in this topology, this is L2. So you actually put IP destination IP address, but your data is not routed using, suppose A is here and B is here, both are in one subnet. So you put destination IP address just for this B machine so that B's network layer can identify this and do the things. But your data is routed not using the IP address because L2 does not store IP addresses in the MAC table. L2 recognizes B by the MAC address. So within a subnet, your data is not routed or forwarded using IP address. Within a subnet, data is forwarded using MAC address only. Are you getting my point? IP address is needed only when you want to transfer data across the subnet, like in case 2. Okay? Where you need to go to the routing table and use the destination IP address to know the things. Got the point? Okay. Any other question? Yeah. Obviously. Again, if I show you my ARP cache, you can see here that this is 172.132.1. This is my default gateway. Have I shown you the default gateway? See, my default gateway is this. Are you seeing it? And for default gateway, already I have MAC address cached. So the nodes you are communicating, those MAC address entries are made in ARP cache. So I told you the first step to check the ARP cache. If it is not available in the ARP cache, then only you need to run this whole process. Got the point? So I think we can stop here And if there are no more question, you can leave. Yes. Hmm. 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 Let me stop the recording.